Okay, good afternoon, everybody, and welcome to our fifth, I would say, remote seminar. And our distinguished guest today is Denis Erkal, who's actually the first remote speaker, meaning speaking outside of Bologna, basically. He's calling us from the University of Surrey in the UK, and he kindly agreed to give us this seminar. So just a brief introduction. Denis got the PhD from the University of Chicago in 2013, and then he moved to Cambridge, UK, for a postdoc, and he is now lecturer at the University of Surrey starting from 2017. And he will tell us today about the stability and the dance of the Milky Way and the Large Magellanic Cloud. So please, you have 20-25 minutes. I will tell you when 20 minutes are passed. Please.
Okay, great. Thanks, Franco. So, can everyone hear me well? Hopefully, I think Franco, we've been talking, so hopefully. And you can see the mouse on my screen?
We can.
Great. So yeah, so thanks. It's great to have an opportunity to chat in this coronavirus era. Nice to talk about science. So today I'm going to tell you about the dance of the Milky Way and the LMC. And so this is a nice picture from Gaia DR2 with the kind of glorious Milky Way, stretching across here, and this tiny little LMC and SMC. And hopefully by the end of this talk, I want you to appreciate that the LMC is actually massive and actually a huge satellite of our system. So the motivation for this talk, you might think, the LMC and the Milky Way. The motivation is that the LMC is the Milky Way's largest satellite. It has a stellar mass of about 3 × 10⁹, so relatively modest in the scale of 10⁻12 solar mass Milky Way. It's about 50 kiloparsecs away right now, so it's quite close to the Milky Way, well within its spheral radius. And it's a very rich system on its own, with a lot of cool stuff that you could study just on the LMC. And it's on its first approach to the Milky Way right now. So today is the time when it's has kind of just recently gotten the closest. And so why should we really care about the LMC and how big it is? Well, you might say that puts the LMC in a cosmological context, helps us understand where it came from, helps us understand its properties as well, how many stars it has, its gas, its satellites. But the big question I want to really focus on today is it big enough to affect us, the Milky Way? Because this is what is kind of really near and dear to my heart is the Milky Way. So the question is, can the LMC really affect the Milky Way or not? And so the reason this is interesting is that we have lots of predictions in lambda CDM and various other dark matter models. So in lambda CDM, we predict that halos are triaxial. So we have this flattened shape for the Milky Way halo. Various models like SIDM can affect that. So self-interacting dark matter takes that triaxial shape and makes it slightly rounder. The Milky Way mass is also very important. If you want to know the mass of the Milky Way, that's important for understanding the context of our own galaxy. And the question really is, how are these affected by the LMC? And is the Milky Way even in equilibrium? And this is just a plot to talk about the shape of the Milky Way. So this is a plot by Sami et al. 2018 showing the axis ratio, which is the kind of how flattened the Milky Way is. So one is that it's spherical, and this red band shows the prediction of lambda CDM with baryons. So you expect a relatively flattened halo, and this blue line is what happens when you add self-interacting dark matter. And so if we can measure the shape of the Milky Way, that would help us, understand, is it CDM, is it lambda, is it SIDM, self-interacting dark matter? And the real question I'd like to understand is, how does the LMC affect our ability to even answer these questions? Because this is at the heart of understanding what dark matter really is and our own galaxy. So that's why I'm talking about the LMC at all. The mass of the LMC in the past was actually quite low. By the past, I just mean human history, not its own past. So in 1992, Sharma et al. Measured a mass of 1.5 × 10⁻10 solar masses. So still very modest compared to 10⁻12 for the Milky Way. Rotation curve measurements by Van der Marel et al. Gave us 1.7 × 10⁻10 at 9 kiloparsecs. And recent work with Gaia DR2 gave 1.4 times 10 to the 10 at 7 kiloparsecs. So all these numbers were about, let's say 1/100th the mass of the Milky Way roughly. But there was a bunch of indicators that perhaps it's actually much more massive than that. So when you look at the LMC, you see material really far out from the LMC. So this is a plot from Mackey et al. And you see there's this substructure 15 kiloparsecs away from the LMC. This could be due to interactions with the Milky Way or the SMC, but it shows this stuff really far out. And we see these kind of debris fields around the LMC, suggesting that it's actually quite big, bigger than we initially thought, perhaps. You can also do some simple calculations that were done, suggesting it's actually much bigger. So with abundance matching, which is when you match the stellar mass to halo masses in simulations, you get a mass of 2 times 10 to the 11. Now, that's pretty big. That's about 1/5 the mass of the Milky Way or so. And if you ask what it takes for the LMC and the SMC to pull in together, you also get something like 10 to the 11 solar masses. It has to be more massive than 10 to the 11 in order for the SMC and the LMC to have been bound in the past, to have fallen on the Milky Way. So what I want to do today is present more evidence, more direct evidence that the LMC really is this massive, and then what that does to the Milky Way to answer the questions that I first brought up. So this is the picture from Gaia, and just if we wanted to put the LMC at 8 kiloparsecs, roughly where the Milky Way center is, it would be this big. So this is just trying to drive home the message that it looks a bit small in the sky because it's pretty far away compared to the Milky Way, but it's actually a pretty chunky galaxy in its own right. Okay, so I'm going to talk today mostly about different ways of measuring the effect of the LMC on the Milky Way. One thing I'm going to focus on first is streams, so stellar streams, then on the effect of the LMC on the stellar halo, and then some last brief discussion on other effects that I can't fit into these 25 minutes. So tidal streams. Tidal streams are ubiquitous around the Milky Way and many external galaxies. They form when objects disrupt on orbits around our galaxy. And so what happens is a dwarf or globular cluster orbits, stars get ripped off from the Milky Way tides, and those stars roughly follow the original orbit of the progenitor. And so what you get are these relatively straight paths on the sky that are mostly staying within a plane. So for example, this is the well-known Sagittarius stream. This is the Orphan stream. PAL 5 is down here. So when you look on the sky, you see all of these relatively straight features following great circles. And these are streams. And they're great because we can use them to measure the potential of our galaxy. And this goes back to the first questions I asked about how triaxial is the Milky Way, what's the mass of the Milky Way. And so streams have long been thought of as one of the great tools to do this. And so now we're going to see how the LMC is affecting streams, and we can learn from streams about the LMC and our own galaxy. So this is the Orphan stream. So the Orphan stream is this one I showed you just here. Here, this is a small part of the sky, but with Gaia DR2, we found Orphan stream stars here in white over a very large part of the sky. And so this is a very long stream. And you can see that this part of the stream passes very close to the LMC, at least on the sky. And Orphan is moving this way, roughly, and the LMC is moving this way. And so you could imagine in the past, they were much closer than you might think from this image. And that's indeed what's happened. So now let's take a look at some data on the Orphan stream. Again, the motivation is to use it to measure the mass of the LMC. So this is a plot showing the proper motion of stars in the Orphan stream. So these black points here are the same stars I showed you earlier. This is the stream on the sky in coordinates that are aligned with the stream. So that's why it's relatively a small range on the y-axis. And these arrows show the proper motion direction of the stars in the stream. And what you see is here on the left-hand side, which is the part close to the LMC, there's this huge misalignment in the direction the stream is moving and the orientation of the stream. So for a stream on its own, we would have expected that these arrows roughly point along the stream. But there's this huge misalignment here. On the right-hand side in the north, the error bars are actually much larger. So actually it's consistent with being aligned on the right-hand side. On the left-hand side, it's extremely misaligned. And the only way to get this is by adding in something which really perturbs the stream. And so we use this stream to measure the mass of the LMC. So this shows a kind of set of naive fits just to get a sense of what's going on. What we did here was we fit the stars on the right-hand side, and then we saw what happened on the left-hand side. So if we have no LMC, so again, this is the track on the sky in the top here, this is the stream on the sky, and these are other observables that we got from Gaia. So we have distance and proper motions and RA and DEC. And on the bottom is radial velocity, which were not used in the fit, but just give you a sense of whether we're roughly in the right ballpark. And so if you have no LMC in the model, you can do fine in the north where it's far from the LMC, but in the south, you're really, really off. And it's not possible to bring this stream up here while getting the other observables correct. But if you just take this best fit in the north and you add a pretty big LMC, about 10 to the 11 solar masses, it pulls this part of the stream up, and you can match almost everything just by just putting it in there. Of course, accounting for the orbit that it's on. Then we can do a full fit with the LMC, with the Milky Way, all three parameters, and we can fit for the mass of the LMC, for the mass of the Milky Way. And this is our best fit model, which requires a LMC mass of 1.4 times 10 to the 11. And you can, these arrows show the direction the stars are moving in the simulation. And this is a very good match to what we see in the data. And these are the other observables. So distance, proper motion and RA, proper motion and DEC, and the radial velocity. So we have these great, yes, go ahead.
I have a small question. I'm not an expert here. When you introduce the LMC here, is that like a point like, I mean.
So the LMC is introduced as a rigid Hernquist profile, which is following the orbit of the LMC around the Milky Way.
Okay, good. Thanks.
So it's, so it's rigid, it's not deforming, but it's an extended profile. But again, it's not allowed to deform in the presence of the Milky Way. And so this gives us LMC mass of 1.4 times 10 to the 11 solar masses. And to give you a sense of how that happened, this in black here shows the present day data of the orphan stream. And this blue, these blue particles are a simulation of the stream forming in the presence of the LMC. And for a while, the stream follows the stream follows the orbit. But at the very end, you can see the LMC comes in and basically pulls the stream away from its orbit. So we have this blue cloud going around, which is the tidal debris, which formed from the previous pericenter. It's following this orbit, which is in black. But then the LMC comes down and it kind of causes the stream almost to skid off its original trajectory. And this is the offset that we're really seeing. So this blue, this black dashed line is the orbit. So normally the stream would have been on that orbit, but the LMC has pulled it severely off its orbit. And that's what we're seeing in the data as well. So this has allowed us to measure the mass of the LMC. So this is the first measurement, the kind of first direct measurement of something like the total mass of the LMC. And we get 1.4 times 10 to the 11 solar masses.
And sorry, and the potential of the Milky Way is static in this case?
No, so the potential of the Milky Way is also a rigid potential, which is allowed to move in the presence of the LMC. So we have the LMC and Milky Way as basically individual particles that are sourcing potentials, but the Milky Way in response to the LMC. And I'll show you how much the Milky Way has moved in these simulations. So basically, these simulations are, they were tuned to match N-body simulations. So we think the motion of the Milky Way and LMC around each other is accurate based on N-body simulations, but the actual fits are done with individual particles representing the Milky Way and the LMC sourcing their potentials with dynamical friction included with formula.
Thank you.
And so this shows the typical triangle plot. What I want you to take away from this is that we're fitting everything at once. We're fitting the mass of the Milky Way, the scale radius of the Milky Way, the mass of the LMC, and we're also fitting for the shape of the Milky Way. So when we do this, we allow the Milky Way to be not traxial, but axisymmetric. So we allow it to flatten in an arbitrary direction to try to measure this traxiality. Of course, these are just axisymmetric fits to the halo. Now, what I'm not showing here, there's many other dimensions to this fit, including the proper motions of the LMC, the distance of the LMC, which all have strong priors, but they're still part of the fit. So really we have about 20 parameters in the fit. But this just shows you the ones that are the most physically interesting. And what I want to draw your attention to, number one, that we're measuring the mass of the LMC here. This gives about 1.4 times 10 to the 11. But most interestingly, perhaps, is this bottom right two triangle plots. So what this is showing is the orientation that the halo is asking for. So remember, the Milky Way is supposed to be triaxial. Here we have an axisymmetric halo, but it's preferring a particular direction. And this red point shows the direction to the LMC. So for some reason, our halo is asking to be stretched towards the LMC, in addition to the mass of the LMC, which is directly affecting things. These fits are requesting a halo which is aligned with the LMC. And we get two different alignments when we do this. So if we have an oblate halo with Q less than 1, the halo asks to be flattened within the orbital plane of the LMC. And for a prolate halo, it asks to be stretched towards the present day LMC. And so this is a sign that something perhaps is missing in our model. So this is very similar to what Lomachevsky found when they fit the Sagittarius stream. So they did not include the LMC, but they found the same shape with the halo asking to be flattened within the orbital plane of the LMC. And so this is a sign perhaps that something is going on, and that the LMC is actually doing something in our halo or affecting our ability to measure the shape of our halo. So the flattenings that we see here are actually much more extreme than what we see in the predictions of lambda CDM. So this might suggest that the Milky Way has an extremely flattened dark matter halo, which would be cool. But more likely, we think, is that our models aren't capturing the full effect of the LMC. And so now we're looking into models where the Milky Way and LMC deform in the presence of each other. So these panels here show an N-body simulation of the Milky Way. So the left panel is cross-sections of the Milky Way in the XY plane. And this middle panel is the LMC, and the right panel is a total. And so what you see is that, and these red points are the orphan stream. And so what you see is that the Milky Way is, in these simulations with a massive LMC, the Milky Way is slightly distorted by the LMC in these N-body simulations, but the LMC is very distorted. So this, again, this is the density contours of the LMC. So perhaps this really weird halo shapes we find is a sign that the LMC itself is distorting, and perhaps the Milky Way as well. So the next steps for us are to include these effects now and to test if the deformation is important for the streams. And it's not just the orphan stream. Many of the streams in the sky show these velocity offsets. So if you compare the proper motion with the stream track, you get these very large offsets. So again, these are a bunch of streams here. The black lines show the orientation of the stream, and these blue arrows show the proper motion direction. And this is the LMC here for context. And you can see that a lot of these streams have proper motions that are pulled off their track and kind of aligned with the direction to the LMC roughly. And so right now we're in the process of repeating the orphan fits for all of these streams. And we're roughly finding the same mass as orphan. So almost all of these streams are consistent with a mass of about 1.4 times 10 to the 11, though there is a pretty wide spread. But we are finding a consistent picture over the whole sky in the south. And just to put those streams in context of the shape I showed you earlier for the Milky Way. So again, this is the Gaia image. All of these dots here show stars in different streams. So the streams we're finding the biggest effect for from the LMC are, as you might expect, these streams in the south. So these streams here, this orange, red, pink, green, cyan, these are the ones where we're seeing a big deflection by the LMC. The ones in the north, we don't see much of an effect. And so right now we're trying to fit all these streams simultaneously to measure the Milky Way and the LMC. And these are streams from this S5 survey by Lee et al. 2019. So actually what I haven't told you is that every single colored dot here is a star in the stream with radial velocity information as well. So we basically have 5D information, so proper motions, radial velocities for all of the stars that are colored. Not the white ones, these are our Lyra, but everything else has radial velocity information. So we have a lot of information to fit That's what we're currently working on right now. So now there was a question earlier about, what do we do with the Milky Way? Well, the Milky Way is allowed to move, and it moves quite a bit. So this plot here shows you basically how much the Milky Way has moved in these simulations. So this blue line here shows the distance between the present day Milky Way and what it was in the past. So this is 2 gigayears ago, and this is today. So it moved by about 60 kiloparsecs. Thanks, Franco. And this is the velocity offset of the Milky Way from what it used to be. So we have this huge velocity shift of about 40 kilometers a second in the center of the Milky Way. And now you can use this motion to try to figure out what stars should be the most affected by the LMC. And this black line here shows you the orbital period of stars versus their radius. And so basically stars that are on the left-hand side here have very fast orbits compared to the effect of the LMC. So we expect stars within about 30 kiloparsecs or so respond adiabatically and kind of coherently to the LMC perturbation, while stars on the right basically stand still as the LMC falls in. We have this impulsive regime. So what we expect is that the inner 30 kiloparsecs of our galaxy roughly are in equilibrium, and beyond that, there's going to be large velocity offsets. So I'm going to show you what this means for the stellar halo. So as the LMC comes underneath, it basically pulls down on the Milky Way, and there's a region inside here where the orbits are very fast. The stars are whizzing around, and they basically respond in bulk coherently. And we're living in this area. So what we should expect to see is that we're moving down relative to most of the outer parts of our galaxy. And so this was some simulations now by Garavito Camargo showing the vertical velocity of stars over the whole sky at 70 kiloparsecs in simulations. And what they expect is that there's this large bulk upwards velocity from their simulations, which had a slightly different LMC mass to what we fit for. But what you get is, again, this kind of bulk upwards velocity. And this is because effectively we've been pulled down relative to the galaxy. And we made our own simulations of the same thing. So here we show the proper motions in kind of left to right in longitude, and the vertical proper motions in latitude, and the radial velocity signal of our simulations of the stellar halo. And what we see is that within about 30 kiloparsecs, most of these plots are mostly white. So most of the averages are 0. So over the whole sky, we shouldn't see much within 30 kiloparsecs. But as you go beyond 30 kiloparsecs, you expect to see a lot more bulk motion. So everything should be moving upwards. In radial velocity, we should see large dipoles on the sky. And hopefully Gaia DR3 will be able to measure this. And so we're predicting this kind of bulk upwards motion for all of the outer part of the Milky Way, roughly. It's not exactly that because there's some small effects directly due to the LMC. We also predict overdensities of stars behind the LMC. So this top panel shows the density. This red line is the orbit of the LMC. And what we see is that there's an overdensity of stars predicted in the outer part of the halo. And we've actually found this overdensity already. And so here, this is observations of the outer part of our halo inside different coordinates. And what we see is that there's an overdensity of stars right here, and that's exactly in the place of the overdensity predicted due to the LMC. So this is the wake of the LMC we're seeing in our halo. And we can use this to do a lot. We can use it to measure the way the LMC is orbiting our galaxy. We can hopefully use it to measure things about dynamical friction in our galaxy. But the point is that we're already seeing these large effects in the halo of our galaxy. And we also see in this wake, we also see this velocity offset, where almost all the stars in the wake, on average, have a negative radial velocity as predicted, because they're effectively moving towards us, because we're moving down through the halo of our galaxy. And so we're getting this kind of picture now where all the observations agree with this picture of the LMC falling in. And one other nice thing we see is if you look at the globular clusters and satellites of the Milky Way, if you look at them beyond 30 kiloparsecs, what you see is this bulk upwards motion. So this is a simulation of the prediction of the average velocity of stars in the outer part of our galaxy. You can see the X and Y velocities are mostly 0, independent of the LMC mass. But the Z velocity has this very large positive velocity of about 40 kilometers a second. And we see that in the data. So if you look at the dwarfs beyond 30 kiloparsecs, X and Y velocities on average are 0, but the Z velocity has a large positive Z velocity. So we think we are starting to see these effects in the outer part of our galaxy. So I think with that, I think I will wrap it up, but I'll just quickly show this slide to give you a sense of other things that I didn't have time to talk about today. So there's many other things we think the LMC is going to do to our galaxy. It's not just the stellar halo and the streams. It's also going to affect the number of satellites in the Milky Way. So we've now found 7 LMC satellites that fell in with the LMC. It affects the dark matter velocity distribution locally. It changes the orbits of satellites around the Milky Way. And it also affects hypervelocity stars and their trajectories from the Milky Way center. And so this is the kind of coherent picture we're seeing now. And so in conclusion, I hopefully I've shown you some evidence that the LMC really is big, and it's having a big effect on our galaxy. So it has a mass of about 1.4 times 10 to the 11 solar masses, which is roughly a sixth of the mass of our galaxy. We're finding these really weird shapes for the halo. We think these are likely due to additional effects we haven't accounted for. Many of the streams in the shell show perturbations, and we're seeing this non-equilibrium features in the halo now, where the inner 30 kiloparsecs or so are in equilibrium, but beyond that, roughly, it's out of equilibrium, and we're moving down through the halo of our galaxy. And so we think the Milky Way is not in equilibrium beyond about 30 kiloparsecs. And it gets worse and worse the further that you go. But that was a relatively quick talk with a lot of details, so hopefully you've gotten at least something out of it. So thanks for your time.
Okay, thanks, impressive. I had already a request, so you have one question from Carlo at least.
Very nice, very nice talk. So I wanted to ask, so how much the fit that you presented at the beginning of the talk is robust, neglecting the effect of the SMC, for example?
Yep. Yeah, so I think, so my answer to that is that when you look at things like H1 data, you see that there's a very big Magellanic stream in H1. And the best models for that is that the SMC itself has been disrupting for a while around the LMC and has stripped a lot of its material already. When we look with radial velocities at the SMC, we see that there's kind of no coherent motion. It looks as if the SMC itself is fully disrupting right now. So the answer, I would say, is that we think that the SMC has been around the LMC for so long that it's disrupted most of its dark matter already, and now it's disrupting its stars. So any dark matter the SMC contributed is effectively in like a torus or perhaps even a halo around the LMC. So this mass that we're giving here is some effective mass, which combines the LMC mass and the bulk of the SMC's mass, which is, we think, already stripped and already orbiting the LMC.
Perfect. Then we have Antonio Solima.
Okay. Hi, Denis. Nice talk.
Hi.
I have a question because now your results are very interesting, but they are based on a very complex fit of all the dynamics of the external dynamics of the LMC. While these results conflicts with the internal dynamics measures, so the rotation velocities of the planetary nebula and other satellites. So how can you explain this discrepancy? Because it seems that the internal dynamics should be much more robust than the external one.
Great question. So when we put in, so first of all, these internal dynamics are all measured where there are stars. So this is relatively close to the LMC. So these mass measurements are all made at 9 kiloparsecs or 7 kiloparsecs. So this really is the inner part of the LMC. Every single mass that we use for the LMC in our own fits matches these mass constraints. So basically, what we're seeing from the data is just the very inner part of the LMC with these direct measurements. But the LMC goes on way beyond that. So expect a flat rotation curve, and that goes out pretty far, we think. And so basically our LMC models already match this data because we require, like part of our fit is matching this. And so this is just the very inner part of the LMC, because the LMC's real radius is something like 100 kiloparsecs. And so these measurements at 9 kiloparsecs are basically measuring just the inner part of the galaxy. Like if you were measuring the Milky Way mass within, 15 kiloparsecs or 20 kiloparsecs, you only get a fraction of the total mass.
Okay, thank you.
Okay, and then we have Carlo Nipoti.
Okay. Hi, Denis. Thank you for your talk.
Hi, Carlo. Thank you.
Yes, I have a question. I mean, this estimate that you make of the mass of the LMC,
Yes.
consistent with the stellar to halo mass relation for galaxy or that stellar mass?
Yeah. So the abundance matching measurement is about 2 times 10 to the 11, but that's a kind of very simplistic one. But yeah, but it is consistent with the stellar mass halo mass relation. So yeah, just this one here. So yeah, basically abundance matching would give you 2 times 10 to the 11 for the LMC, but that has a pretty big error bar on it.
Okay, thank you.
Okay, let me check. I don't think, no, there are no more other questions. So I think that's it. Thanks a lot.
Great, my pleasure.
Thanks to everybody that joined, more than the usual. I'm very happy about that. And okay, now I will stop the recording now. And the next talk will be next Tuesday. And I wish everybody keeps safe at home. And thanks, Denis, again for being our guest today.
My pleasure. It was a lot of fun. Hopefully it was enjoyable for everybody.
Mm-hmm.
Happy Easter as well to everybody.
Thank you. Thanks.
Bye.
Bye, everybody.